Well, welcome back to the third week. I guess you are a bit exhausted. It must be intense to be in your position. Luckily, I am in my position. We're going to start with a deep message, which is what is the title of this topic, which is gravitational waves. Oops, what's going on? Oh, no. This is not working. Felix, sorry. This is jumping slides. Which one is it? This one?
It should be just this.
No, it's jumping slides.
You're at the beginning now.
Yeah, now. Okay. Okay, sorry. So, these are called the object of our study, gravitational waves, and not gravity waves. It turns out that gravity waves mean something else, in fluid dynamics. Still, there are papers where people write gravity waves instead of gravitational waves, referring to the ones we're going to talk about. The ones we're going to talk about are normally written with the acronym GW. So let me start with a motivation. And the motivation is very simple. These are very special times, and we should really celebrate this. Why is that? Because gravitational waves are being continuously detected. And this is literally a milestone, both in theoretical physics and in astronomy. We should literally take 1 minute, of silence to really, celebrate this, but the clock is ticking, so let me move forward. Please appreciate that it took us 100 years, and I don't think there is any example in physics similar to this, 100 years from a theoretical prediction until its discovery. Good. So, what have we learned so far? That there are plenty of order 10-ish solar mass black holes, that there are also neutron stars there, less than we thought. We can test the paradigm of black holes and neutron stars. We can furthermore test the underlying theory of gravity. So far, no deviation whatsoever of general relativity. And furthermore, we can observe the universe with gravitational waves. And you might be thinking, well, how do we do this? We can do it studying binaries, and essentially we study the waveform of these binaries, and this is why we are celebrating the fact that we can do this, even though the prediction was back to 100 years before. And you might be thinking, why am I going so fast over all of this? No, this should be the content of the talk. Actually, it's not. This is extremely interesting, but this is not going to be the focus of this series of talks. We are rather going to focus on this other aspect, the fact that we can observe the universe. Okay? And I highlight the universe. First of all, let's highlight observe. This means detection. Okay? We can literally see, detect. That's what it means, this new tool, which are gravitational waves. And let me highlight the universe, because this is very important. We are going to try to do what with gravitational waves? We're going to try to do cosmology. If you think of cosmology, you can think of late universe cosmology or early universe cosmology. Late universe deals with the structures in the universe or the equation of a state. So you could do the program of standard sirens, measuring distances in cosmology, H0, equation of a state of dark energy, and whatnot. But, again, this is not the focus of my talk. Here, in this series of lectures, we are going to rather focus on the early universe, on the high energy processes that actually create gravitational waves. Does that mean that I'm going to forget about the late universe? Actually not. In order to give you a complete picture, we're going to have to take it into account, but we are going to postpone that to the very end. Good. So let's focus on the particle physics part. So the question or questions that motivate this series of talks are the following. Can we really prove high energy physics using gravitational waves? And if so, how? Okay? Answering these questions is precisely lies at the heart of this series of talks. Now, answering these questions is precisely what I'm going to be telling you about in this series of lectures, but before we enter into those answers, let me ask another question, which is the following. If gravitational waves can be used as a proof of the early universe, let me ask to you now, why? Why should I even think about this as a case? And to give you a hint, there is one and only one reason. Anyone? Yes?
Because the universe was
Sorry, say it again, I don't hear you very well from here.
Because the universe was transparent to gravitational waves way earlier than the photons.
Okay, and why is that? What's the reason for that?
Because they are not energetic.
Not really, it's not related to energy. Yes?
Well, the couplings are so weak that they decouple it.
Exactly. It's because of the weakness of gravity. This is the key point. So let's exploit this. The weakness of gravity is really the key point here. Because gravity is so weak, gravitational waves are going to decouple immediately upon production, which is what our colleague was saying. But the reason is really the weakness. At the same time, this is a disadvantage. This is why it took 100 years to detect gravitational waves, because these are an extremely weak phenomena. Good, but let's take advantage of the idea that if we produce them, they are going to probe the early universe because they are going to decouple. So whatever properties, say the spectral shape of their spectrum, will be retained and will be specific to whatever high energy process. So for each high energy process, I will have specific predictions of gravitational wave backgrounds. What are these processes? These processes in the early universe. So let me start by introduce you to the early universe. By early universe, I think you've been covering this in previous lectures. I literally mean the first second of the universe, whatever happened before Big Bang nucleosynthesis. I believe Yvonne Wong has covered these ideas. I'm not sure to what extent, but let me very briefly just say that I'm going to assume there is a period of inflation, of exponential expansion. There is a period of reheating following afterwards, where the energy responsible for inflation gets converted into particles, which eventually decay into other species, and altogether, eventually they thermalize, passing to the thermal era, the standard hot Big Bang picture. We are going to assume this picture. And now the question is, what phenomena are interesting within this second that we can probe? Well, we are going to deal with quantum fluctuations in inflation, typically, with non-perturbative particle production, either in inflation or reheating, possible phase transitions, this typically requires beyond the standard model, and possible cosmic defects, which are a very interesting possible consequence of a phase transition. What do all these guys have in common? They are very different phenomena. What do they have in common? The first thing they have in common is just the title of this series of lectures. They emit gravitational waves. That's why we are going to be talking about them. But furthermore, why are we talking about these guys, that they emit gravitational waves and not nothing else? Any clue? What is common to all these phenomena? Besides being high energy physics phenomena, these are nonlinear phenomena. And because of this, the production of gravitational waves is going to be extra strong. And that's why we think of these phenomena and not others. Because in a sense, anything produces gravitational waves. The question is, what are the phenomena that produce sufficiently strong gravitational waves that we have a minimum chance to detect them? Good. So suppose we produce these gravitational waves, they freely propagate. They are going to come in the form of backgrounds because they are produced everywhere in the universe. So we will refer to this as cosmological gravitational wave backgrounds, cosmological because they come from the early universe. And they are a unique cosmic messenger that if we manage to detect them, it will carry unique information from these processes. Absolutely unique. So they are a unique proof of the very early universe, and hence the big interest there is in the community to explore these two. What can we measure with them? Well, sorry, unfortunately this thing jumps transparency sometimes. We can probe energies way above terrestrial means. We can probe fundamental physics and beyond the standard model physics, which otherwise are inaccessible, and we can get as close as possible we will ever get to the origin of the universe, whatever that means. So it is a unique opportunity to study this. Typically, when we talk about this background, we can classify them in 4 categories, which come in a chronological history of the universe, so the inflationary period, pre or reheating, phase transition, and cosmic defects. So essentially, these are the categories we are going to cover of the early universe. Good, but what about the late universe? I mentioned before that maybe there is something to scratch there on the late universe. After all, what we've measured about gravitational waves are astrophysical gravitational waves that come from the late universe. No? We've measured a lot of binaries. These are all the binaries we've measured? Not really. In reality, we've only measured very few of them. And from them, we infer that there is a very large population of other binaries that by themselves are weak enough for us to detect them individually. However, the red ones realize this, represent these ones that are very weak to be detected. So most of the binaries in the universe in reality are unresolved. This doesn't prevent them from emitting gravitational waves. So we expect that if you put together all the signals, they are going to form what we call an astrophysical background. So necessarily there's going to be such a signal also in our detectors. Good. This is from black holes, neutron stars, or white dwarfs, whatever compact objects we can have in the universe. So altogether, this is the picture of gravitational wave backgrounds. Now let me give you a perspective of what is the situation, a summary in a sense. So gravitational wave backgrounds can be either of cosmological origin or astrophysical origin. The first one's from the early universe, the second one's from the late universe. The first one's prove high energy physics, the second one's the distribution of binaries in the universe. So the first ones are the holy grail of gravitational wave background astronomy. Because if we measure them, that's how we are going to access to the fundamental physics behind these signals. But the second one are guaranteed background, because we already know there are binaries. And it's going to be there. They are going to be there no matter whether we like them or not. So they are going to act as a foreground for the first type of signals that contain the fundamental physics. And hence, in the whole program of detecting gravitational wave backgrounds, in particular the first type, cosmological, we are going to have to deal with everything together. Good. So the core of my lectures are going to deal with the early universe sources as backgrounds that prove fundamental high-energy physics, but in a peripheral manner, we will also have to cover the astrophysical ones, just because they are a contaminant. Okay? Sorry if there is any astrophysicist in the room, no offense. It's just that for us it's really a problem, unfortunately. Good. Talking about gravitational wave backgrounds, nowadays is a complicated thing because it requires that you know about particle physics, about gravity, about cosmology, and about astrophysics. Okay, it's really complicated, and of course I don't know what are your backgrounds. Maybe some of you consider themselves particle physicists, or others consider yourselves cosmologists, or gravitational people. I don't know. I cannot guess what is the level of each one of you. I'm going to try to make an effort to be as pedagogical as possible. Okay, and as I was saying before, the core of the lectures are going to be based on these cases. So we are going to discuss gravitational waves from inflation, preheating, phase transition, and cosmic defects. But what kind of lecture would this be if I do not define gravitational waves themselves? So in reality, we're going to have a first lecture that's going to be today on the actual definition on gravitational waves. And that's going to be on the theory part. And then, as I said, to give you the complete picture, the overall view, we are going to have to deal also with late universe and the experimental side. So we are going to discuss, although more briefly, astrophysical backgrounds and observational constraints towards the very end, depending on time. Good. This first topic, the topic of today, is going to be a theoretical formal topic. It's going to be a bit complicated. It depends on your level on GR, how easy you will follow it or not. This main set of topics will be on the Fino theory side. And this I'm going to build on the idea, on the advantage that I know Oliver already gave you a lecture on phase transitions. So that topic I'm going to cover in a much more superficial manner, and I will dwell much more on the others. Oops. And finally, maybe let's consider it as a bonus. As I said, we will also consider astrophysical backgrounds and observational constraints. So all in all, I'm going to try to give you a complete picture of the game that we are playing in gravitational wave backgrounds. Good. Lecture of today, gravitational waves. So now we know the real title of these lectures are gravitational wave backgrounds, and the first lecture is a primer on gravitational waves. Good. The underlying framework I'm going to use for gravity is general relativity, which I assuming you are familiar with. So we are going to use Einstein equations, G mu nu equal T mu nu. I like to use the reduced Planck mass, and we are going to use contractions of this kind all the time, and emphasize that general relativity is a theory invariant under general coordinate transformation, also known as diffeomorphisms. Good? That's our starting point. Now we want to define gravitational waves. So Einstein equations are a complicated second-order nonlinear differential operator over the metric, sourced by the energy momentum tensor or whatever is there in the universe, from matter radiation to topological defects, dark energy, whatever you want. How could we start thinking of defining gravitational waves? Well, we are going to take a perturbative approach. We are going to think there is a background, and I can think of perturbations on top. And that's what we are going to exploit, the idea we're going to exploit. Good. Of course, not every part here will source gravitational waves, so we will have also to deal with the matter part to understand what part of it is really a source of gravitational waves. So, perturbative approach. I really hope you got good doses of coffee, because you are going to need it. There are going to be really many indices here, okay, just to anticipate. But we are going to take 3 different approaches in order of complexity. So the first one is the textbook one. Hopefully most of you are familiar with it. And then we will start adding complexity into the picture. Well, first definition of gravitational waves, this is the textbook one, and is the one I don't like at all. I just have to give it because it's in every textbook. But I personally don't use it at all. But let me start with it in case somebody is not really familiar with the concept of gravitational waves. First approach consists on taking a metric, G mu nu, and consider that this is just a perturbative deviation from Minkowski. So I take Minkowski as a background, and I take a perturbation on top, which I assume is much smaller than 1 in absolute value, which means much more smaller than any entry of the Minkowski metric. That's what it means. Good. This is called linearized gravity. For reasons that you will see in a moment, we are going to linearize all our theory to first order in perturbation theory in this guy. Good. Very important to emphasize, to highlight that this is Minkowski. Okay? This approach of linearized gravity is based on fixing the background to Minkowski. And that means that we are fixing the frame of reference. So essentially, I'm already breaking this full diff invariance symmetry, unfortunately. It's not there anymore. What I have instead is a residual symmetry, or if you want, an infinitesimal version of it. Essentially, what is that? You can make an arbitrary coordinate transformation, but small enough such that you don't spoil this configuration. If the derivative of this guy are smaller than the metric components, this is how the metric components, the perturbation transform, then I don't spoil this decomposition. I'm still in Minkowski background plus perturbation. So this is still a diff invariance, but it's an infinitesimal version of diff invariance. Good? Notation. Notice that I'm using this parenthesis here. This is the symmetrization notation. This is anti-symmetrization notation. Okay, I'm going to use that quite a lot. Good. Let's now expand Einstein equations, which means I'm going to introduce this guy in my Einstein tensor, or in my Einstein equations, and see what comes out. In order to do it, it's more clever to define this trace reverse guy, which is this definition, which is called like that, just because the trace of the h bar is the minus trace of the original perturbation. So once you define this trace reverse tensor, essentially after some algebra, this is what you get from plugging this in your Einstein tensor. You get a complicated operator of this form with many derivatives sourced by the energy momentum tensor on the right hand side, and this is the first order expansion of the Einstein equations. If you want to work on gravitational waves, or you are already working in gravitational waves, I really strongly recommend you do this exercise for one time in your life, which is to do this expansion, just to first order, okay? Good. Now, this equation, differential equation, will be a bit difficult to solve it, but remember that we have infinitesimal diff invariance, so let me exploit it. I make a change of coordinates in such a way that now I impose the Lorentz gauge over my metric perturbations, in particular the trace reverse ones. This is just a choice. It's a specific type of family of coordinates where I verify this thanks to my gauge freedom in the theory. Imagine that I'm in a frame where this is not the case. I'm not in the Lorentz condition gauge. Well, no problem. I make a transformation of coordinates. I transform now to the new tensor perturbation like this. And now I impose over the new guy that this is vanishing, its divergence. The original one is not vanishing, that was our starting point, but to make all of this vanishing is very simple, because all I have to do is to solve this equation, which is a wave equation over this perturbation. And a wave equation always has solution, okay, with a source. So essentially, if I'm not in the Lorentz gauge, I can easily go into a system of reference which has the Lorentz gauge. Why is it useful? Because just look at the form of equations here, of these two terms. Essentially, these are vanishing in this gauge. So I make a clever gauge choice such that I remove these terms. Voila, this is how the equations, first order perturbed Einstein equation now looks like. What is this? A wave equation. So we are getting where we want to, right? Good. Notice that from the original 10 degrees of freedom, now I have 6 degrees of freedom. I'm removing 4 just because I have this condition, which are 4 conditions in reality. Okay, so I only have, presumably, 6 independent degrees of freedom at this point. Good. Is that all? Well, not really, because I still have a residual gauge symmetry. And this residual gauge symmetry is just making this transformation, but now imposing that the box operator on the vector displacement here is 0, which is the same as saying I'm going to jump from a Lorentz preserving gauge to another system of coordinates, which is also Lorentz preserving gauge. So Lorentz gauge framework is a family of a system of reference, not just one. Okay? I can make another one. I can impose this. Now I have 4 conditions, 4 extra conditions. And let me assume, for simplicity first, that I'm outside any source. There is no source anymore. Well, I can take this extra freedom, 4 conditions, and impose that all the 0 components of my perturbations are 0, and that the trace is 0. Plus the Lorentz condition that now takes this spatial form. Okay, that was already there. What is this? The transverse traceless gauge, the famous transverse traceless gauge. Why I don't like all of this that I'm telling you? Because it gives the impression that to define gravitational waves, I need to go to a specific gauge, which is what we are doing. Let me stick to that, but you will see later on that that's not really necessary. Good, so in this gauge, the equation is the same, it's a wave equation. Now over this Hij guy, but now I have 2 degrees of freedom, because out of the original 6, I discount another 4 from these 4 conditions. So now I am in the picture that you've always read, you know, in your undergrad book before you started reading seriously about GR. There are 2 degrees of freedom. No, the graviton has 2 degrees of freedom. That's the manifestation of this aspect. Good. What about if there is a source present, or I am surrounded by a source, whatever way you want to picture it? Can I take the transverse traceless gauge? Anybody? Any clue? Because the answer is only yes or no. You might guess it by chance. So the answer is no. If you are in a source or with a source around you, you cannot take this transverse traceless gauge simply because, for instance, demanding that this 0 component is part of the gauge would imply that the corresponding 0 components of the energy momentum tensor have to be 0. And the matter doesn't know anything about this gauge. So I cannot necessarily demand this. So essentially, in general, I cannot take the transverse traceless gauge. Okay, this is not a generic gauge I can take. Yet, you know, precisely for this example, I cannot make this choice. But yet, I can still describe my equation of motion like this, where I have apparent 6 degrees of freedom, but in reality, 4 of them are redundant. There are still only 2 fundamental degrees of freedom. It's just that I cannot make them manifest them explicit. You see, again, this is why I don't like this formulation, because now I can show you that the same equation, a wave equation, propagates apparently 6 degrees of freedom, when in reality 4 of them are redundant. Good, anyways, let's think we are in vacuum, and I can take my outside a source, so vacuum, no source. I can take my TT gauge, transverse traceless gauge. This is how it looks, the problem. Wave equation, relativistic wave equation, and hence the name gravitational waves. Okay? Which also tells you that gravitational waves at this level are only a phenomena at perturbative level. You know, very different from electromagnetism, where I have electromagnetic waves no matter what. Here, I'm only in perturbation theory in order to define them like that. Can they be gauged away? Well, it turns out that no, because we've already exploited all the gauge freedom we had. Now there is no transformation I can do to remove into less than 2 degrees of freedom the 2 degrees of freedom I have in the TT gauge. Good. How do they look, gravitational waves? Well, the Lorentz condition already tells me that they are transverse to the direction of propagation. I choose Z as an arbitrary direction, and the gravitational waves is something that can only live transverse to the direction of propagation. Plus, they are traceless. There are 2 degrees of freedom, the polarizations. So let me write now this tensor that lives in the transverse plane as a decomposition of all the modes that satisfy the wave equation, which are plane waves. Okay, basic second year undergrad physics, nothing special, but just living in this transverse plane with a tensor. Good, so we want to decompose our full tensor field in the transverse plane into linearly independent components in some tensor basis, and I know that in general my field, my tensor field, has to be traceless. Therefore, I immediately consider this situation, and also has to be symmetric because these matrices are symmetric. So this is actually the general form, which immediately tells me what is my tensorial basis of independent degrees of freedom. And this defines the plus and the cross terms, polarizations, which essentially, if you have a set of test mass particles and you get a gravitational wave going through them, and there is only the plus mode, this is what it's going to do to your ring of test particles. Okay, it's going to squeeze it one direction, then in the transverse one, and so on and so forth. And for the cross term, it's going to do pretty much the same, but in the diagonal, which tells you that cross and plus are in reality nothing special. I can rotate my system of reference and turn my cross into plus and the plus into cross. All right? They don't have a meaning individually, they have a meaning when the two of them are decomposed and separately superimposed. Good. Who among you were familiar with these ideas? Okay, a significant fraction, but not everybody, not everybody. Good. Let me go into the second definition of gravitational waves, a definition that I really like much more, because as you will see, now I'm going to make it gauge invariant. I'm going to remove this problem of the gauge freedom in general relativity to give a more proper definition of what I mean by gravitational waves. Are there any questions anyway so far about the first approach? Everything clear? Or not, simply people don't want to ask? Good, second approach. Let me start again by decomposing a generic metric, well, not fully generic, but situation in which I still can have Minkowski on the background plus perturbation, again smaller than 1. And now this perturbation, I decompose it into what we call the scalar vector tensor decomposition. What this means is to do this kind of association. To the 0, 0 component, you associate a scalar. To the 0i component, you associate a vector, but also a gradient of a scalar. To the ij component, you can associate a scalar here, then a double gradient or Laplacian of another scalar, then derivatives of a vector, and then a pure tensor. And the same you can do with the energy momentum tensor. Okay, same idea. Good. Let's put them here on top. And let's count the number of degrees of freedom. So I have a scalar, vectors, and tensor. This means a scalar, vectors, and tensor with respect the group of transformation of O3, of rotations, which is a group of transformation in Minkowski. No? Physics is rotationally invariant, doesn't depend on the direction of observation. So, how many scalars do I have? For the metric perturbation, I have one here, another one here, and then two in the spatial part. Okay. What about the energy momentum tensor? I have one in the 0, 0 component, another one in the 0i component, and again two in the ij component. What about vectors? I have one vector here, 0i component, and another vector in the ij component. Pretty much the same in the energy momentum tensor. And then I have a pure tensor here in the ij component and a pure tensor in the tij component. Good. So all in total, counting degrees of freedom like this, I have presumably 16 degrees of freedom, which are the entries of a 4x4 matrix. But of course we know that the matrices have to be symmetric, so there should be 10 degrees of freedom. So in order not to overcount degrees of freedom, we need to impose some constraints. And the constraints we impose are that the so-called vectors here, like Si for instance, or Fj there, they are divergenceless. So we impose a scalar constraint. And the so-called tensors, the Hij, are also divergenceless and traceless. And now you may ask, where does this come from? Well, it turns out that if you impose these constraints, mathematically you can show that this decomposition is B-univocal, is unique. Okay? You could think of imposing other constraints, then that wouldn't be a unique decomposition. Okay? But if you do these constraints, then now I'm subtracting all these degrees of freedom here, 1, 1, 3, and 1, so 6 in total. I'm going to have 10 degrees of freedom there. And the decomposition is unique. The same I can do for the energy momentum tensor, and now you can, 6 degrees of freedom in each. This constraint represents 6 degrees of freedom. Then I remove 6 degrees of freedom. So I'm literally left finally with 10 degrees of freedom on each side, the metric and the energy momentum tensor. Good. Now, let's use some other physics here. I know, for instance, that the energy momentum tensor is conserved. Of course, notice that I'm using ordinary derivatives and not covariant derivatives. That's because I'm in Minkowski. Okay? Otherwise, you will have to do this with covariant derivatives over a background. Physical constraints. Well, energy momentum is conserved. Very good. This implies, if you plug in the decomposition you have for the energy momentum here, this can be rewritten in 4 conditions, which are these constraints. One constraint for this scalar, u, here. Another constraint for this other scalar, sigma. And a constraint for this vector, vi, which are 2 constraints because this is a vector equation and it's divergenceless guy, so it's only 2 constraints. 4 in total, which means I can subtract these 4 degrees of freedom in my counting, and then I'm left with 6 degrees of freedom. Okay, 6 degrees of freedom, the counting is getting better, no? Because we started in 16, now we are at 6. What about the metric degrees of freedom? Well, now the game is not so easy because my decomposition, it's imposed at the metric tensor level, but this constraint, the equivalent one that we used before, is at the level of the Einstein tensor, not at the metric tensor. Okay? So essentially we cannot play the same game, let's play another one. Let's exploit, again, the symmetry we really have underlined in my theory. I make a transformation of coordinates, generic one. Then I transform the metric perturbations, generic transformation. Remember, just a small diffeomorphism, so these guys are small. And now let me decompose this displacement vector in the same fashion I've been doing so far. So with a scalar for the 0 component and a vector and gradient of a scalar for the spatial part. I'm just decomposing it in the same manner that I've been doing so far with the other guys. So this vector here is divergenceless. If you do it, immediately now you get to translate the transformation of coordinates in GR, the infinitesimal diffeomorphism, into what it means for the scalars, vectors, and tensors. So essentially, this is the rule of transformation of a generic coordinate change of coordinates, infinitesimal diffeomorphism, in terms of these variables. Good? You don't really need to look much the details, well, other than realizing that, of course, what is this? 4 degrees of freedom, you know, because I have 4 degrees of freedom here. So again, I subtract 4 degrees of freedom and I'm left with 6. So now the counting is on equal footing, and it should be 6 left-hand side, 6 right-hand side. Good. But the very important thing that I want you to put attention is that this guy didn't transform. It's already gauge invariant. So this is telling us that pure tensors are gauge invariant, which are giving us a hint already of they are going to play a special role for us. I can, of course, also make gauge invariant scalars and vectors by making now linear combinations, because I know these transformation rules, and if you work it out well enough, you will realize that this linear combination with time derivatives will give you a scalar that is gauge invariant. Same here, and same for this vector, which is also divergenceless. So all in all, at the end, I can write all my degrees of freedom now in a gauge invariant manner, which is, of course, a much more convenient way of thinking about physics. How many degrees of freedom? One scalar, second scalar, vector, which is 2 degrees of freedom because it's divergenceless, and tensor, which is 2 degrees of freedom because it's transverse and traceless. Okay, 6 degrees of freedom, 6 gauge invariant degrees of freedom. If I have achieved this, what is the next step? Well, let me find a way to write now my Einstein tensor in terms of these guys. And that's what I'm doing there. So essentially, we are able to express now the Einstein tensor, the Einstein equations, in terms of these gauge invariant degrees of freedom. And if I can do that, which is this expression, you don't need to look into the details, I can write then the Einstein equations, the perturbed Einstein equations, in a gauge invariant fashion. And in case you are not appreciating how amazing this is, really, guys, I'm writing now the full perturbation theory in a gauge invariant manner. I give you a monkey, you know, for you to understand that this is something really amazing. And every step we find something really cool, you will get a monkey, okay? So essentially, let me summarize what we are doing, because this is really non-trivial. I never learned this during my PhD, you know. It had to take a number of years until I find a way to understand this, because it's not written almost anywhere. There is a way to write your gravity theory in such a way that your perturbative degrees of freedom are gauge invariant directly. And look what you are seeing here. What kind of equations do we have? Let me plug them here. We have Laplacian type of equation, Laplacian type of equation, Laplacian type of equation, and propagating type of equation. So essentially, now we see that the tensors, the transverse traceless degrees of freedom of my metric decomposition, are something very special, because they are the only degrees of freedom that are being propagated, because they are the solution to a wave equation, as opposed to a static Laplacian equation. Okay? So essentially, only radiative degrees of freedom, because they satisfy a wave equation, are the only degrees of freedom that were already in first place gauge invariant, which are the tensor modes. So gravitational waves can be defined as these tensor perturbations directly, no matter in which gauge you are. This is precisely the whole point of all of this, that it doesn't really matter, obviously, in what system of coordinates you are, to define the concept of having the notion of gravitational waves. The previous definition was a weird choice of coordinate, of system of coordinates, where as co-moving observers with, in that kind of system of coordinates, we were making explicit that our degrees of freedom were only the transverse traceless degrees of freedom. Here I can be in a generic system of coordinates, and I will have a scalar and vector degrees of freedom in my metric perturbation, but only the pure tensors will represent the gravitational waves. So I only have to care about them. This is precisely the idea of this. Okay. Questions? Who had seen this ever? 2 people? 3, 4? 5, yeah, okay. Of course, ideally, I would like to show you this in a generic background, but then that would take too long, you know, so I'm gonna show you instead something in between, which is the third definition of gravitational waves, which is of my own making, in a very specific background, which is the one of cosmology, Friedman, Lemaitre, Robeson, Walker. Okay, that's what we are gonna see next. How are we doing with time? Do we want, oh, question, sorry.
So I didn't exactly catch why Laplace type of equation isn't propagating.
Okay.
Can you give?
Sure. Because Laplace type of equation has no time. You know, it's purely spatial derivative operator, that's why. So essentially that's a constraint equation. It's like once you have a hypersurface of initial conditions with your fields defined, amplitudes, then they are not going to be propagating. They just have to be satisfied spatially. But the only one that is really being sent away is the wave equation. Because the wave equation, as the name indicates, sends waves, you know. Yeah. Question?
How can we be sure that, like, if we go to the full theory and not only the linear one, will we still have, like, a wave-like behavior?
Okay, very good question. Let me repeat the question actually because they told me, and I forgot with you, sorry, that I have to repeat the questions. How can we be sure in a context where the physics would be non-perturbatively, so I have to take the full nonlinear GR, that the equation is wave equation? Well, the answer is that the equations there are not wave equation, are the Einstein equations, which are not wave equation, are nonlinear field theory propagating phenomena, extremely complicated. And this is why it took so many years also to solve fully, numerically, the two-body problem, the simplest case you can think of, two black holes orbiting around each other. Okay, because it's extremely complicated to solve even that, let me call it simple problem. Now, what happens is that at the source level, so around the black holes, surely you cannot describe them like this. You have to do the full GR solution. But eventually, once you get sufficiently far away, the fields are gonna decay just because of distance propagation, and then I'm gonna go back to this picture. So at our detector level, it's always this picture, you know, on Earth. But at the source creation of the phenomena, surely you have to follow all the degrees of freedom. However, you know that a combination of them eventually are the ones that are going to impact in the transverse traceless degrees of freedom in the far away distance, you know, and that's what people do. Yeah. But this is very interesting comment because it shows you that gravitational waves in reality, in a sense, is a bit of misleading name because the actual creation of, let me call them gravitational waves because there is no other name, at the level of the source are actually not driven by a wave equation, you know, but something way more complicated. And with more degrees of freedom involved in that moment. Yeah. Good. More questions? Okay. If not, how are we doing on time? Do we want to take a break already, or? It's up to you guys. I'm happy to start with the third definition, or we can take 2 minutes break. 2 minutes break, they suggest there. Let's take 2 minutes break. This is of my own making. We haven't put it in the form of a paper yet, so please don't do that in the next month, you know, because it took me a while to develop this, okay? And now I'm gonna give you the full solution. It is still not the ultimate answer. The ultimate answer would be what is the most generic solution or definition in an arbitrary background and what circumstances I need to demand to that metric background in order to define gravitational waves, okay? But now, here I'm going to use a curved background in the space-time sense, which is that of cosmology, Friedman, Lemaitre, Robeson, Walker background. That's what I'm going to assume for my background, and I'm going to assume that I have some sense of perturbations on top. If you don't like this kind of inequality, you could think there is some epsilon parameter here, which is small, that controls the strength of the perturbation. Good. Flat Friedman, Lemaitre, Robeson, Walker is what observations of CMB tell us. The universe is spatially flat. Essentially can be written in this simple manner. It's a conformal metric to Minkowski, where the conformal factor is just the scale factor. And T here represents conformal time. Good? Flat Friedman, Lemaitre, Robeson, Walker plus gravitational waves, I can write it like this, with conformally redefined gravitational waves. As a matter of fact, for almost everything I'm going to tell you next, I don't even need to specialize my perturbations to gravitational waves to focus only on the transversal electricity. I could leave it generic. So actually, forget about this second line and think of it as generic perturbations. And I will tell you when we specialize them to the tensors. Now, conformal transformation between metrics is when you think of the space-time element like this, of a metric, G mu tilde. G mu tilde is a conformal transformation of G mu, where the conformal weight is the scale factor, and the G mu for me is Minkowski plus perturbation. That's why I'm doing it like this, because now I can use all the power of conformal transformations, as I'm going to show you in a moment. So, okay, have this in mind. This is my full metric. It's decomposed in the product of two pieces. Time-dependent part, the background, and the Minkowski plus perturbation. Good. Einstein equations, they look like this. I like to write them in this other fashion, which is the following. The Einstein tensor is nothing but the trace reverse Ricci tensor by construction, which means that the the trace reverse Ricci tensor equal to the energy momentum tensor, I can use this to convert my Einstein equations into Ricci tensor equal trace reverse energy momentum tensor. Good? Where the trace reverse name, remember, it simply reflects that they have opposite trace, nothing else. Good, so I'm going to write my Einstein equations now in this fashion. Ricci tensor equal to trace reverse energy momentum tensor. The question I want to solve is, what is the Ricci tensor of a metric, G tilde, which is conformally transformed from another metric? And now I remind you what is the mathematical expression for the Ricci tensor. It's given by this complicated form in terms of Christoffel symbols. So there are derivatives and there are products of Christoffel symbols. Let's remember our notation. I'm going to use this parenthesis, curved parenthesis for symmetrization of indexes and square brackets for antisymmetrization. So essentially I can write in a more compact manner my Ricci tensor in this manner. So at the end it's not so scary, there are only two terms, linear term with derivative, quadratic term, product. Good? And the Christoffel, remember, is nothing but these derivatives over the metric times the inverse metric here. Good. Let's put this on the top. Now, remember that my full metric, the G tilde, is conformally transformed with respect to another metric, which is the Minkowski plus perturbation. This is the advantage of working in the flat Friedmann-Lemaitre-Robertson-Walker, that I can exploit what I did before. Question, shall I use the blackboard? I'm somehow jealous of Seida before. Do you prefer I use the blackboard? Who prefers the blackboard? Oh, a lot of people, but not everybody. Okay, I'm going to do something in between. I'm going to create my own blackboard. So, essentially, we are going to use the blackboard, but it's still here. So, we have to compute the Christoffel of this full metric. And look, if this is the functional form, given that the Christoffel, it has this form, it's this quadratic form, necessarily the answer to this must be the Christoffel of the old metric plus the formation. I don't know if you see that directly by eye, but this has to do with the fact that this is a product. And because this is a product and this is a product, the only way I applying this definition to the Christoffel is to get the original Christoffel plus a deformation. And this deformation can only depend on the original metric plus derivatives on this weight factor, which now I take as the natural log of omega, which remember is just the scale factor. Okay? I don't pretend you do on the fly that calculation, but if you think a little bit about it, you'll see that that's the only answer possible. Good. Let me pass it there. This little omega is nothing but the log of capital omega, which is nothing but the scale factor. How, if I know this, and this is the answer, the formation of the Christoffel is just this linear expression in derivatives of the little omega. How does it look the Ricci tensor? Well, the Ricci tensor, remember, is derivative over my Christoffel plus product of Christoffels, which means immediately I can rearrange this into the original Christoffel, forget about the deformations, plus whatever deformation of the Ricci, which can only come from the deformation of the Christoffels. It's clear. So let me put it here. The deformation of the Ricci, it can only be first derivative of the deformation of the Christoffel, deformation of Christoffel times Christoffel background, vice versa, and then product of deformation of Christoffels. Just from the definition. You know, it's very basic math what I'm doing at this point, but there are many indexes that make it a bit more confusing. How does it look, this expression? Any guess? Imagine you are mathematicians, and I don't want you to do the algebra of this. I just want you to think of the symmetries and ask you what is the functional form of this guy. It can only depend linearly on little omega and bilinearly in little omega. First clue, okay? And it has to be a tensor. So I have to build tensors out of this little omega, which means there is only a one functional way to take derivatives over them such that I build the answer. And the answer is this. It can only take this functional form, where omega mu is nothing but the derivative, the normal derivative of this omega. This is the covariant derivative. Okay, sorry, they are defined here. These are the ordinary derivatives. And this is the covariant derivative. Well, if you don't see this, don't worry. You can also do it explicitly. You plug in the Christoffel deformation here. You do your algebra, and this is what you get. You get this expression with the actual number of the coefficients. Actually, to my knowledge, the only way to get the coefficients is to do the calculation. It'd be great if somebody is clever enough to tell me a way to figure out the coefficients without doing the calculation. I didn't manage. I managed to get relations between them, but not all of them. So probably it's not possible, but who knows. Good. Imagine we've done the calculation, and now we know this deformation. It is this, you see, 4 forms of involving derivatives, ordinary derivatives of the conformal weight, which now I put explicitly as the log of the scale factor. Then there are covariant derivatives, which have this definition in general relativity. Good. Let me change notation. This delta r mu nu, which is all of this, let me call it now like a differential tensor operator over little omega, where the operation it does is all of this. Different terms can be computed explicitly. It's actually very simple because you only have to plug in this little omega and take actually normal derivatives or covariant derivatives. So first term is the most trivial one, is just proportional to the Hubble rate squared, which I put with curly because I'm in conformal time. Second term is a bit more complicated, it's covariant derivatives, so it has background derivatives, Hubble rate squared, A prime prime, and then it has a cross term between background and perturbation, or if you want and Christoffel, sorry, because this comes from the covariant derivative. Third term is just again simple. It can only have information of the background, but is multiplied by the metric, and the metric has information of the perturbations here. Fourth term, sorry, covariant derivative again times the metric. The metric again has metric perturbations, and covariant derivative brings me here the Christoffel. Again, I don't pretend you to follow the exact details, but the exact details are given here if you want to do it offline. Let's put them here on the top, and let's recall that the definition of Christoffel is the inverse metric times the derivative of the metric, and the metric we are using right now is Minkowski plus perturbation, so derivative of Minkowski 0, then derivatives are only on the perturbation directly. Which means this term is already first order, necessarily. Which means the lowest order I'm going to have of a Christoffel of this kind is going to be first order. And the metric inverse, the inverse metric, I can actually easily expand it in perturbations. In Minkowski, this is very easy to do. To first, second order, arbitrary order. I plug it here now. And then I count orders. I have my expansion of inverse metric, 0, first, second order, etc., times something that is always first order. So the first order Christoffel is necessarily the product of the Minkowski guy here times these derivatives. The second order is the first order of the inverse times the derivatives, and so on and so forth. Okay, so again, I'm building explicitly all the terms. Since I'm only interested going up to second order, I keep these expressions. So first order is like the definition of Christoffel with inverse metric of Minkowski here. Second order is the definition of Christoffel with the perturbations. Good. So let me plug them in here, that my Christoffels that I had here have first order and second order. Let's review now term by term. Sorry, maybe am I doing something here? Yeah. I'm going to write now my deformation of Ricci, which remember is this expression, which is given explicitly here. Now I'm going to classify it into zero order, first order, and second order. So, zero order, all these terms, whenever the metric perturbation is not involved, the background, Minkowski times background, okay, they are highlighted in red. First order, all the terms that involve either directly the metric perturbation or Christoffels to first order. Second order, all the terms that involve the metric perturbation times Christoffel of first order or Christoffel of second order directly times the background. Okay? There is no more in those expressions. As complicated they might look, all the information is there. So let's say we've already managed to write down this in full detail. What about expanding the Ricci tensor in a Minkowski background? Well, it turns out that we have everything we need to do that, because all you need is the Christoffels of the deformed metric of Minkowski plus perturbation, which we know already to first and second order. We just did it a moment ago. So I plug in that. Remember, this is the functional form. First derivative plus bilinear. I plug it here, then first order, second order in the derivative, first order, second order in the product times first order, second order. I rearrange terms, and first order there can only be the derivative, and second order there can be derivative or product of first orders. Anything else is higher order, so I should discard it for my purposes of going to second order. I could go to nth order here. I can do the full nth order perturbation theory just writing the other terms. You know, I'm just discarding them because I don't need them, but everything is there in the formalism. Good. These tell us that there is a first order deformation of Ricci and second order deformation. Of course, the zero order, the background order is zero because that was in Minkowski. So now we have everything, I think. I plug it here, there is zero plus first and second order deformations with zero first and second order deformations of the tensor derivative operator, because we did the conformal transformation. We put it like this. Maybe it's more clever to arrange now everything in order, zero order, first order, second order. Good? Okay, just repeating zero order, it only comes from the conformal transformation. First order comes, however, from both conformal transformation and the expansion of metric perturbations on top of Minkowski or on top of a background. Second order, the same. Now, up to here, what I've shown you is valid to all perturbations. Let them be scalar vector tensors. So the h mu nu was not specialized to anything. But now let me specialize it to transverse traceless degrees of freedom, because we know those are the ones to be identified with gravitational waves, with the propagating degrees of freedom. So now I want to create just the theory of my gravitational wave degrees of freedom, but you would have everything if you want to create your theory of the full gravitational perturbation theory. Okay? We are simply going to specialize to transverse traceless degrees of freedom because we already learned that in this decomposition of a scalar vector tensor, the tensor part are the gravitational waves. Good. Zero order, we put together what we derived before, and of course, it has only background information, Hubble rate, and second scale factor derivatives. First order, now it has to be linear in the tensor perturbation. Remember, I'm specialized in TT parts, otherwise I would have more terms here. So you have this kind of derivative operators over Hij. Second order has to be bilinear in the metric perturbations explicitly, and then there is the Ricci tensor to second order, which we already know comes from derivative of second order Christoffel and product of first order Christoffels. Let's forget for the moment of second order for simplicity. Let's focus in zero and first order. Good. So zero order has to be related to the background clearly. First order has to be related to the propagation of these guys. Let's focus on the Einstein equations. Let's plug in these guys into the Einstein equations, which remember I like to write as Ricci equal trace reverse energy momentum tensor that I call S now. Plug in our ansatz, which is we are in zero order plus first order, and here are the expressions here. Then we are going to need zero order and first order on the matter on the right hand side. And the equations are going to split naturally into background order and first order. We already know the left hand side because it's written explicitly there, but now we need to work out the right hand side, the matter part. Now in cosmology, because I'm in a Friedman, Lemaitre, Robertson, Walker background metric, we describe the background energy momentum tensor by a perfect fluid. You are more familiar with the T mu expression. This is the trace reverse expression of a perfect fluid. And on top of this, I can add an anisotropic stress if I have something that perturbs that energy momentum tensor. Actually, not only this guy is a perturbation, be aware also that I have naturally another perturbation embedded already in the functional form, because I have the metric here, which has directly a perturbation on the metric itself. Okay, so I have two types of perturbations. So I separate now between background with no perturbation and the perturbed part, that linearly on the metric and on the anisotropic stress, which plays the role of perturbation here of first order. Yes, question?
Why is this anisotropic stress only spatial?
Well, so why Ij? Oh, simply because, no, this is a typo, of course, no. I could think of pi mu nu, but since I'm specializing my computation into the transverse traceless degrees of freedom, which only have Ij, then I'm going to keep only the Ij part. But sorry, this is a typo. At this level, it should say mu nu, okay? But, and I'm afraid that was the origin of the typo, because I can decompose any one mu nu actually into a scalar vector and tensor, and the tensor only have Ij, then the idea was to keep Ij only, okay? Because now this guy is only my tensor, my transverse traceless degrees of freedom. Good. So, sorry, yeah, I see I'm mixing the indexes everywhere, but it's what I'm saying. Background, well, any more questions up to here? So, background equations, left-hand side, right-hand side. Now we know everything. I plug them, I put explicitly the functional form, and this is what I get. Some linear combination of Hubble rate and second derivative equal linear combination of energy and pressure background densities. What is this, guys? Do you recognize it? I sum them, oops, my God. I sum them, I subtract them, and voila, these are the Friedman equations. So you see, we are doing something right, because in our decomposition, we haven't spoiled the background. And we are really getting what we ought to get, we should really get, which is the Friedman equation describing the evolution of the background. Okay? These are the Friedman equations in conformal time, hence the minus here. Okay? Not a typo. First order part, more interesting. So, left-hand side, first order expansion, that we did all the effort, and right-hand side, first order in matter. Voila, this is how it looks. I have what it looks like a wave equation, but I also have this, like what it looks like a mass term. What happens, yeah, if this didn't anticipate the transparency, is this really a mass term of the graviton? We know, of course, that the graviton doesn't have a mass term. What's going on here is that this guy is actually going to balance exactly with the, once I plug in the Friedman equations here, with this other term. And this shows you that when people claim that expanding the Einstein equations give you the wave the Einstein tensor, sorry, in Friedman-Lemaitre-Robertson-Walker, give you the wave operator, this shows you that they've never done this calculation. Because if you just do that, what you get is a mass term. It is absolutely mandatory that I pick up the piece of the perturbations from the background energy momentum tensor. Okay? Otherwise, this guy would be there, and that's not what's happening in reality. They have to cancel out, and they balance out exactly. And then what we are left is with the gravitational wave equation. I give you a little monkey, because, okay, this is some achievement. Probably you are familiar with this equation, some of you. This is now the same as I had before. Instead of a Minkowski, now I have a wave equation in an expanding background. The difference, there is a friction term with the Hubble rate. I'm in comoving time, remember? Conformal time, sorry. So that's why there is no scale factor here, and that's why this is curly H. And this is the transverse stressless pair, the tensor part of the anisotropic stress. That's the source of gravitational waves. Okay, so again, this is good achievement because we might have known this from other sources, no? And this is looking good. Friction term, because we are in a cosmological setup. Good. So, third order Friedman equations, first order propagation, equation of motion of gravitational waves. Then, what about the second order? What can I do about this guy? What do I want it for? Can I do something interesting with it? Second order, Ricci tensor looks like this. Explicit bilinear term plus the formation of Ricci to second order, which is this form, with the first and second order Christoffels given here. Good. How does this look like? Let me, instead of showing how it looks like directly, let me now go to more fundamental principle, and let me go to the Hilbert-Einstein axiom. Why? Because this is written in terms of the Ricci scalar. The Ricci scalar is nothing but the trace of the Ricci tensor. And we already know the Ricci tensor. So I'm rather going to put together the inverse metric here with the element of the determinant, and I'm going to call this F mu nu. Good. So now I'm going to write my Hilbert-Einstein axiom like this. And recall, very important, what I'm going to show you now is only for the TT parts, although, again, you could do it for all the other components. The F mu nu is the product of the square root of the determinant of the background metric times the inverse metric. And essentially, to first order, the determinant, the square root, sorry, to second order, it has this expression. And the inverse metric, again, to first and second order, it has this expression. So I can put it together into 0, first, and second order, just rearranging them. Good. Why am I doing this? Because now I can write the Hilbert-Einstein term as a product of two guys that I know how to expand to 0, first, and second order, which immediately implies I can write to 0, first, and second order the Hilbert-Einstein axiom itself. I do it, and this is the formal answer. The integrand in the first case is only 0 times 0 order. Integrand second case, 0 to first order, first to 0 order. Integrand in second case, 0 to second, first to first, second to 0. Cannot be other possibilities. Good, but we have the answer to all of this. Now I plug them in, and voila, this is what it gives. This gives 0. Exercise, question to you, you don't need to answer now, but in the next class, why that gives 0? It has to be to give 0, you know, and actually if you do it, it gives 0, but why? There is a reason of symmetry. 0 order could only describe the background, of course, but very importantly, second order now has a Lagrangian on second order on this guy, Hij, which is the transverse stressless degrees of freedom. So now I have an axiom that describes the dynamics of this guy, like if it was a field that lives in the Friedman-Lemaitre-Robertson-Walker background. And that's what I'm going to exploit. I'm going to use this to play around with it and extract information. So second order Hilbert-Einstein term has 3 terms. The first consistency check we are going to do is, of course, it should provide the correct equations of motion for the tensors. Before we did it by expanding Einstein equations directly. Now I'm going to do it from expanding to a higher order, second order the action, and now do variational principle. So you do variational principle, and voila, what you get here is our good old wave operator, as usual, in expanding background, plus, again, a seemingly mass term, which through the Friedman equations, through the background equations, I can relate to the pressure. Again, this shows you that if you were to do the equations of motion only from this piece, from the second order Hilbert-Einstein, then you wouldn't get just wave operator, you would get the mass term, as before. Why is that? Because, of course, we are missing, again, the matter sector. If you really want to do the full exercise, you have to deal with the matter sector, even if you think you are in vacuum. Eh? And this means that I should be able to write this in 0, first, and second order. And if you do it explicitly, this is, oops, this is by construction, how it looks. This is the definition of the energy momentum tensor, the first variation. Then there is the functional derivative of the energy momentum tensor, which is the second order in the metric expansion. And I could go as any order I want. I stop in second order. Now I specialize to my transverse traceless degrees of freedom. And if you plug in here the T mu nu from the perfect fluid plus anisotropic stress, essentially here, because you already have first order, the only thing that survives is the anisotropic stress. And here, because you have second order already, the only thing that can survive is a background quantity, which actually is the pressure. But this comes from the computation, if you were to do it explicitly with the perfect fluid form. Good. So this is my action to second order for matter, has 2 pieces. Now variational principle, and I get source, tensor part of anisotropic stress times variation, and then the pressure times this guy. And voila, what happens again? That by consistency, these guys are eliminating each other. So you see, again, if I had not taken into account the fact that there was a background with perturbation, these wouldn't cancel out each other. If you do it, however, they cancel out each other exactly, and what I recover from putting these 2 pieces together is the consistency check I wanted, that the variational principle, the minimum least action principle, tells me that this is the equation of motion of the gravitational waves, which I rearrange a little bit, putting out the Planck mass here, and I have my wave operator equal to the source. Okay? So, again, consistency check pass. Okay? This is non-trivial because remember where we are coming from a second order expansion of the Hilbert-Einstein action, you know, where you have cross terms that don't look like they are going to give the correct answer. But the correct answer is really obtained once you plug in consistently the expansion to second order everywhere, both in the Hilbert-Einstein term and in the matter sector. Good. So, if this guy is related to second order, things to second order are typically what an energy momentum tensor. No? If you compute the energy momentum tensor of any field theory situation, those are typically bilinear expressions. And I have a Lagrangian already of second order of my tensor field living in a background field. So let's exploit that idea. I have total action, second order matter, second order in gravity. And this literally means that I have a Lagrangian for this guy, which is a tensor field, transverse traceless, that lives in this background. So I can think from the point of view of this perturbation of the space-time itself, like if it was an external field that lives in my background. From this point of view, I'm entitled to do it. Let's do it. Let's apply the Nether theorem. Nether theorem tells me that there is an energy momentum tensor associated to a bilinear Lagrangian like this. The Lagrangian is what we wrote before. But Nether theorem doesn't fix completely the energy momentum tensor. That's what most people typically forget, that actually there is certain freedom. I can always add the divergence of a 3 form that is antisymmetric in 2 in the indexes. Unfortunately, Nether theorem doesn't fix completely the energy momentum tensor, but it fixes the charges when you integrate in a space on these expressions over sufficiently large volumes such that the fields vanish in the boundary of these volumes. So essentially, to get rid of this guy, what we typically do is to take a volume average. You can think of the tensor modes, your gravitational waves, as having typical wavelengths. If I take a volume sufficiently large to encompass all its wavelengths, then essentially I'm going to get rid of this because it's going to be a boundary term. And if my fields are sufficiently fastly decaying in the boundary, then this is not going to weight anything. So this is the way to remove that term by doing this trick of the volume element. And funny enough, in electromagnetism, you also do the same, but they simply don't teach you this explicitly typically. Well, if you want to ask more about this, I'm happy to discuss with you. It's subtle, but at the end, if you want to make a gauge invariant definition of your energy momentum tensor associated to your tensor modes, which are gravitational waves, you are mandatorily in the need of doing a volume average when not even a time average as well. Because I could think the same problem in the frequency domain instead of in a spatial domain. In cosmology, we think in spatial volumes, but in the detector, we think of frequency domain. So you can think of this as a space-time volume average, even though I'm only saying volume. And the point is I have the expression of my Lagrangian, so I can compute explicitly now what are the functional forms corresponding to this Nether energy momentum tensor, and I get a kinetic term, a gradient term, a cross term, and an interaction term. Good. Let's put them here. The energy density, the energy density is going to be associated to the 0, 0 part, and is where I get these 4 guys. So the energy density of gravitational waves is the volume average of all these quantities. But now at sub-horizon scales, which is where I'm going to define gravitational waves in any cosmological context, this guy is always subleading versus the Laplacian, for instance, here, or the time derivative, necessarily, because it has 1 less power of k. So at sub-horizon scales, k squared is going to always beat up h times k, or little omega, which is going to be at most k. Good, so I can forget about that term in reality to define in any sensible manner gravitational waves in my laboratory or their impact in cosmology, because only sub-horizon scales matter. But at the same time, eventually gravitational waves are produced and they are going to propagate freely. So if they are going to propagate freely, there's going to be no more source. So I can take it to 0. So eventually I produce a background, they propagate in the universe. The energy density of the gravitational wave background can only be given by these 2 terms. But if these are free fields, after you ended the emission, the production of gravitational waves, then again they are free, they are plane waves, which means the gradient energy is related to the kinetic energy like this. So essentially they are the same. I can remove one of them and put a factor 2 here, just because they are plane waves. And if you do all of this, you eliminate all of this and put the 2 here, what are you left with? With the expression that you have in textbooks, that the energy density of gravitational waves is quadratic in the first time derivative of the tensor field, and this is literally the energy that is understood to be carried by the gravitational waves at sub-horizon scales and for free fields. Otherwise, I have the other complications to take into account. Okay? Monkey, because arriving to this, you know, is a tour de force. It requires all the second order expressions. The only place I know that they have derived this to second order is in Mayore's book, and he does it in Minkowski. Okay, now you have a derivation in a curved space-time background, which is Friedmann-Lemaitre-Robertson-Walker, and of course it boils down to the same case, specialized to the fact that now I'm in conformal time with the scale factor here. More common expression, well, this is the typical expression. So essentially, what we are learning here is that this second order expansion that we did, what it really is informing us, it's about the back reaction of the perturbations, in this case of the gravitational waves, on the background. But in order to make sense of this back reaction, you have to take this volume average, because of course the wavelength of the gravitational waves here can be much shorter than the wavelength of the background. In this case, the background has no wavelength, actually, it's homogeneous. So in order to make sense, you have to take this volume average again, otherwise you would be comparing apples with oranges. Once you take the volume average, then it's like you are integrating out over the UV modes of this guy in the language of field theory, and then you see what's the back reaction of the gravitational waves on the background. And it's this is the energy density, and I could compute the pressure they carry, and then plug in these expressions in the Friedman equations. This is the more typical expression. If I undo the conformal derivative, the conformal time, and I put it in ordinary time, the scale factor disappears, and I wrote it now in terms of g, the Newton constant. This is the textbook expressions you will find everywhere. Good. Now we could define from this energy density a spectrum, energy density spectrum, and this is precisely the game we are going to do in the next lectures. We are going to explore, these are the core topics, what is the gravitational waves produced in this fashion, following this formalism, from inflation, reheating, phase transition, and cosmic defects. Okay? This is to be continued, but let me just give you a hint. The game we are going to play here is the following. In the early universe, well, we have this situation. Now we have our wave equation sourced by the transverse traceless degrees of freedom of the anisotropic stress, which is the difference between the full energy momentum tensor and the background energy momentum tensor. So the situations I want to play with in the early universe is what are those scenarios in which I have a non-trivial excitation of scalars or of gauge fields or of fermions, which provide a non-trivial transverse traceless degrees of freedom part, which then is naturally the source of gravitational waves. That's what we are going to explore starting tomorrow. Thank you very much for your attention.